We're still working on C basics. We'd gotten to the point where we were talking about the three basic variable types that we'll restrict our attention to, at least at the beginning, where we've got an integer, a whole number, but a double, which is a floating point number, and a char, which is a single character. All of these have limitations, right? The first one, integers, can only represent whole numbers from 2.147 billion to about to negative 2.147 billion. And also doubles can only have about 16 to 17 decimals of accuracy, after which it just becomes garbage, right? We've also seen limitations that 1/3 plus 1/3 plus 1/3 is not necessarily 1, right? And we'll see a couple of other gotchas here as we go along. But before we go along, let me go ahead and cover some stylistic tips here. For example, naming conventions. In general, you should use lower camel casing for variable names. Right? Lower camel casing it's named that way because if you think of a camel, right, it's got humps, and that's what it kind of looks like. The first word, if it's multiple words that is all lowercase. And each subsequent word, the first letter is uppercase, and then everything else is lowercase. And so you can kind of see that it goes up and down, right, with the humps of a camel. We saw that before when we did miles and KMS, right? But those were single words. So consequently, they weren't compound words, and so it just looked like this. An example would be number of students. All right. Rules are that you can include any lower or uppercase letter, numbers, and an underscore, right? Underscore looks like that, right? But may not begin with a number, right? That's just too complex for a compiler to deal with. In general, though, you shouldn't put numbers in your variable names anyway. Because if you're putting a number into your variable name, that kind of means that you've actually got a value in mind for that, in which case you probably want a constant anyway. And you definitely don't want to do something like my variable 1, my variable 2, right? Bad variable names would be my var, or my variable 001, and I need another one, so my variable 002, right? If you look at that and you try to understand what 50 lines down or something like that, and you start looking at what does that represent again, right? You're going to have to go all the way up to your comments or something like that. Again, code should be self-documenting. If you've got a variable, you should name it descriptively, right? Use descriptive names. Right? We haven't talked about variable names yet, have we? Like this? Maybe just in passing, but maybe not like this. Other conventions would be upper camel casing. Now the difference there is that the first letter of the first word is uppercased. Generally, we'll use this much later on when we do cover structures, when you name and user-defined types. Another convention would be lower underscore casing. Right? This is really old school. Right? You'll see this all over the place, including Xi books. You can tell how old the person was that wrote Xi books because they were using this very, very old convention. Now, this convention is still used. I think it's a GNU convention as well. It really doesn't matter again because you're going to eventually follow a style guide. I recommend against using lower underscore casing as well as upper underscore casing, except for in a few instances, because what are you always doing? Well, first of all, if you're typing in all caps, right, then you're locking the caps lock on, locking it off every time you type something, or you're going over and you're holding the shift key down the entire time, you're killing your pinky. Every time you do an underscore, hold the shift key down, go all the way over to the other side of the keyboard and hit that hyphen to get that underscore, right? It slows you down. The lower camel casing convention is the modern convention. It'll save your pinky, it'll save your typing, save you on typing. Now, where did we use upper underscore casing, though? Constants, right? And that is an okay convention to follow because constants are few and far between. right? They're not that common. And so it's okay to use a convention like this to offset and give the idea that this thing is a constant. This thing is different. It's not a variable, right? Let's see. All right. Questions on naming conventions? Otherwise, remember that we are online, so if you have any questions, you can post to Piazza or to the YouTube live chat. Right? Operators. Right? You've seen operators already. Algebraic. Is that right? Yeah. Operators. Right? For example, if I write plus or minus, that is addition and subtraction. Those are pretty straightforward. But on your keyboard, do you have, say, this symbol? Let's see. Time. Oh, no, sorry. I'm going to go into LaTeX mode here. Do you see that on your QWERTY keyboard? No. I mean, you could use an X, but the letter X kind of looks like that thing, but it's not that thing. Right? Do you have that thing? No. Divide, right? Those are the symbols that you use in grade school, and then you quickly throw them away and you just have a dot, or you leave anything off, or you write it numerator, denominator kind of thing, right? We don't have those on our QWERTY keyboard. Consequently, we have to make do with what we do have. So division is going to be a /, and multiplication will be a star, an asterisk. Star, asterisk, you can use either one. Right? In the context of numbers, those mean multiplication and division. And is that a / or a backslash? /. Right? But you also have this other operator, an assignment operator, right? Which is a single equal sign. Right? And we've implicitly used it on line 23. Right? We're going to set KMS equal to KMS per mile times miles. Right? And basically the operation here is that it takes the variable, or expression on the right-hand side and places it into the variable on the left-hand side. Right? So consequently, the left-hand side always has to be a variable. The right-hand side can be anything. It could be a number. We call those literals. Right? If I just write 42, right? Then that's a number. It could be an expression. It could be another variable, etc., etc. Right? It's not the algebraic expression A is equal to B plus 2. Right? That's algebra. This is coding. Right? For better or worse, they chose to use the single assignment operator 40, 50 years ago. I don't even think it was from C. I think it was from other languages. Other languages don't use it. I think maybe Fortran or definitely Maple uses something like this. Right? Because they want to use something completely different, right? They don't want to confuse people with an algebraic expression. Haskell uses a left arrow, which is very descriptive of what it means. Take the thing on the right and put it into the thing on the left, right? Right? That's the arrow going that way. But C and most programming languages still use the single assignment operator or a single equal sign for their assignment operator. Right? Another thing. Right? So here's a question. Is A plus B times C the same as A plus B times C? No. Why not? It has a different order of operations when we've got a nice little acronym to remind us of what the order of operations is in mathematics, which is exactly the same thing as in code. What is that? PEMDAS, right? So remind me what those rules stand for. Parentheses, exponent, multiplication, division, addition, subtraction. And it is left to right on all of those. Now, exponents, we don't have those natively in C. I'll show you here in a second. But parentheses, we have those, right? We have those. We can write as many as we want to change the expression. Yeah?
Are logical operators still?
We'll get to that when we get to conditionals. Yep. And it's left to right. They have the same order of precedence, though. Yeah?
So, C
only have the basic algebraic operators,
Those four right there, yes.
but it doesn't have exponents.
Nope, we'll talk about that in a second. You have to use the math library. Right? So in fact, let's go ahead and get into it. Let's go ahead and do a demonstration here. So if I've got a variable, integer a, right, I'll immediately set it equal to 10. If you want multiple variables, you can do as many variables as you want. Int c equals 30. Now, these are terrible variable names in general, unless they actually represent something abstract, right? The coefficients to a quadratic equation or something like that, quadratic polynomial. If you want to compactify this a little bit, you can do it all in one line. B is equal to 20, C is equal to 30. Right, there we go. However, if you have int c, right, what value is stored in C right now?
None. Null.
None, null, gibberish, undefined. Those are all correct, depending, except for the last one, which is absolutely correct, undefined, right? C does not define a default value for variables. Let's go ahead and test it, though. If I print all of these variables out, what is my placeholder for an integer in printf? Percent %d. Right? B is equal to %d, C is equal to %d, and the line. There we go. And we'll print A, B, and C. And I will compile this and run it. 10, 20, 0. So 0 is not the default value. 0 is magically there because my compiler stepped in and said, I'm going to go ahead and give it a default value of 0. Right? That is entirely compiler and system dependent. It could be gibberish, or we call that garbage. Or another way of saying that it's garbage is calling it dead beef. 0x dead beef. Right? So that's hex speak. Right? Hexadecimal, 0 through 9 plus A, B, C, D, E, F. Right? So you get base 16. So what kind of words can you spell just using A through F? Well, one of those words is dead beef. And that's sometimes used to indicate uninitialized memory, uninitialized values. So always remember, if you do not initialize your variables, then you're throwing the dice. It could be 0. 99 times out of 100 it'll be 0. But that one time that you don't initialize it, then you'll get yourself into trouble. And if you try to add gibberish or garbage or dead beef to something else, like garbage plus 1, what is that? Garbage, right? Garbage plus 2, garbage, right? So if you don't start out at those at those default values that you intend, then maybe something will be provided for you, maybe not. Right? C does not provide default values for variables. Often, the compiler will provide 0, but no guarantees. Yeah, go ahead.
So, would there be any reason why you need to declare a variable without defining it?
If you know that immediately afterwards, before you use it, you're going to set it to something.
But then, that's the case, couldn't you have also just set it?
Potentially, it depends on, does that lead to unreadable code? If so, then don't do it, right? In fact, it used to be in old school C, you had to declare all your variables up at the top of a function. You were not allowed to declare a variable down here. And I can show you that, let me go ahead and declare a variable here, int d, right? And I will go ahead and GCC this pedantically. Oh, no, it's letting me do it. Pedantic std equals gc89. Okay, there we go. So in 1990 and before 1990, it didn't let you do something like this, right? It didn't let you have a mixed declaration down below. And in fact, it didn't even allow you to have these kind of comments before that, right? Apparently, I don't know what that means. But we won't be pedantic about it, right? Pedantic means absolutely strict to a fault, right? So go old school C and be very, very strict about it. No, only very, very old compilers on very, very old like embedded systems would you ever have to worry about something like that. Right? Yeah.
Well, that command you just did, would that be useful for if you were working with a system that was not updated to current standards?
Not necessarily a system that's not updated, but a compiler that's not updated, right? And hopefully you can afford a better compiler.
Yeah.
or at least a transpiler that will take new school C and translate it to old school C and clean it up, and then you can use that old compiler. Right? All right, well, we can also reset it later, right? You can set a variable later. Right? So, for example, I'll set C equal to 42 at this point. Right? You can also set a variable to be equal to another's value. Right? I'll put it like that. C is equal to A. Now, if I print these out again, in fact, I'll change A to be 101. There we go. So I've changed both C and A at this point. On line 19, when that gets printed out, what values will each one have? Hopefully you'd say 101 for A, and you'd be right. But what about C?
10.
A. It'll print, so 10. Why 10? Yeah. What was the value of A at the point that we set it equal to C equal to it? It simply took the value 10 out of that variable and put it and copied it into C. Changing A does not affect C, right? So, pile this. Oops. Oh, what was wrong? Oh, because I'm still being pedantic. All right, I don't want to be pedantic anymore. There we go. All right. We just went in the future 30 years, right? All right, 101, 20, of course, because I didn't touch B. And then C is now 10, right? So you can set it to another variable, value. You can also do things like double R is equal to an entire expression. For example, B times B minus, now how do I do the square root again? SQRT, right? And I need to make sure that I'm bringing in the math library, right? No, it's just B, right? All right, you'll see what I'm trying to do here in a second. You're going to have to help me because I don't remember what it is. Times 4AC divided by 2A. There we go. All right, well, what was I trying to do there? Quadratic formula, right? B plus minus, but can you do plus minus? You can't even do that in math. That's just an abusive notation. It's actually two values, the first root and the second root, right? The plus root and the minus root. So we're going to go ahead and do the minus root here. Square root of B squared minus 4AC. So, do I have exponents in C? Can you do something like this? Nope. It'll compile, it'll run. That has a different meaning. That is a bitwise exclusive OR operator. All right, if you want to learn what that is, go ahead and go read about it. Right, we're not going to cover it here. It's just something else entirely. Right? Yeah, go ahead. Say what? No. Okay. What about a star to the 2? Right. Some languages do allow you to do this. C is not one of them. Right. So how do we get B squared? Well, the easiest way is just B times B. But if you really want to do an exponent, what you can do is POW. POW stands for B, and I'll raise it to the power of 2. Power, right? And that 2 is in the math library. Now, if you're going to do POW to the second, might as well just do B times B. Go ahead.
I'm not sure if I'm doing this one, but I was kind of interested in how you could declare more than one variable.
Mm-hmm.
Does that not require a list?
Nope. We don't have lists in C. We do have arrays. We'll get into that in week 7, 8, or something like that. Right? But then each one is indexed, and it doesn't have an individual name. You have the first one, the second one, the third one, all indexed starting at 0. Right? All right. So what else is wrong with this expression? Hold that thought. I want to fix the other basic stuff first. Can I write 4AC like I do in algebra class? No. I have to have explicit operators here.
You can't imply operators?
Nope, you can't imply operators. Now, if you do something like this, you may or may not get away with it. Why? What is I? Imaginary. Don't do it. Don't play with imaginary numbers. Bring in a library to do it for you. Now back to your comment of order of operations. Is this the correct formula? Do I have B minus square root of the radical on the top and then 2A on the bottom? Nope. What do I need to do to make sure that that happens? Add parentheses. Now, does that fix it?
No.
Nope. Why? Because the order of operations is, yes, this thing gets evaluated, but then it just divides by 2 because that's the next one. and then multiplies by a, right? Is a on the top in a quadratic formula? Nope. So what do? Parentheses. Right. Now, horizontal white spacing, right? Should I put spaces everywhere, or should I keep it all together, or something like that? That's going to be a stylistic choice that's up to you. I wonder what A style would do, though. A style demo. Right? Remember A style? It'll style it for you, right? And then you have to close it and open it. See what it does? All right, it doesn't care about horizontal white spacing either, right? It lets you choose. But just be consistent about it. Question? No? Okay. All right. So we've got that. Let's go ahead and print that out. Printf. I don't know. Percent. Now, what I'm going to print R. So what is my placeholder for a floating point number? LF would be for scanf. You can use it here. I will be in the habit of using it just percent %F here. Right? Okay. Oops. Oh, okay. Square root. It doesn't find it. What we need to do is, and this is a quirk of the compiler and the particular setup that we're using, is to link in the math library. -LM. Right? L stands for link. M stands for the math library, and I have to link those in. I didn't have to do that for the standard library or the input-output library. And if you want to learn, know why, then I can point you to a CFAQ, frequently asked questions on what's the history behind why you have to do this explicitly. But once I've done that, then I can go ahead and execute this program. Ah, not a number. What happened? So, look at this radical right here. Right? We call that the radical, right? I'm remembering that correct? Okay. Whatever's in the square root, right? B squared minus 4AC. Well, let's think about what values gave us that. Well, 20 squared is going to be 400. 101, 4 times 101, we're already above that. So what is this difference right here? Is it positive or negative? Negative. Can you take the square root of a negative number? No. Yes, you can in math, but this ain't math, right? So what ends up happening? Nan stands for not a number, right? It's not a real number. It's now an imaginary number. You really shouldn't even call them imaginary numbers because they are real, right? They pop up all the time in the solutions, but they are complex numbers, right? And we do not have native support for complex numbers. Ergo, it's treating it as not a number. Right? Another number that would not be good to use. Let me go ahead and reassign R here to be log of 0. Right? And let's print that out. Log is the natural log, so base E. So normally you would actually call this ln, but it's not called ln and C. It's called log. Right? What is the natural logarithm of 0? So what does the graph look like? Right? It's this very, very slow growing function, but as you approach 0 from above, where does it go? Down to infinity. Right? As it approaches 0, right, it's already negative. It'll go down negative, 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 negative until it gets to negative inf. So you can have inf, negative inf, nan, negative nan, right? Those are numbers that you don't want to play with. What's infinity plus 1? Still infinity. What is not a number plus 5? Still not a number, right? You can't mix those types with any other expressions. Okay. Once you've got an infinity or a nan, it's over, right? You're just going to pile garbage on top of garbage. Okay. All right. Let's see. Here's more gotchas. Right? So let me go ahead and reset some of my variables here. A is equal to 10, B is equal to 20. Now let's go ahead and create, I'll use the same variable here, is A divided by B. Actually, let me do one gotcha here. So what is R going to be? 10 divided by 0, right? So definitely not a number. Why? Because what is anything divided by 0? 0? Undefined, right? Or, I mean, if you take calc and you as as you approach 0 from above or below of 1 over 0 over x, right? As x approaches 0, then you can say that it does diverge down to a negative infinity. That's not what happens here, right? The entire program died with a floating point exception, core dump, right? So be careful. Don't divide by 0, right? I'm going to go ahead and comment this out so that the program can live on and we can continue our demonstration here, right? So I will note here, though, that division by 0 is undefined. And in this case, on this system, kills the program, right? You can actually set up what's called a trap. And if this ever does happen, then you can redefine what happens instead of the entire program dying. You can say, if this ever happens, call that code over there. That goes beyond what we're doing here, though, right? All right. That should work. 10 divided by 20, right? Or 1 divided by 2. What's that going to end up being? Oh, okay. 0? What should it be? 1/2. Why? What happens? When you have an integer and you add an integer, you get an integer. When you have an integer and you subtract an integer, you get an integer. When you have an integer and multiply an integer, you get an integer. Same thing with division. When you have an integer divided by an integer, you have an integer. So what happens to that non-integer part? 0.5. 0.5 gets cut off, thrown away. That's called truncation, right? When dealing with division and integers, right? Truncation loses the floating point part, the fractional part. Right? Result is 0. Right? So how do we fix that? To fix it, you need to typecast at least one of the variables. Right? So I'll go ahead and leave them as 10 and 20, but I'll show you that it now works as long as I treat one of them as a double. Integer divided by a double is going to be a double. A double plus a double, double plus an integer, it doesn't matter. All of those going, if at least one of them is a double, then the result is going to be a double, and you're good to go. Right? What I've done here on line 42 is I've said, for the purposes of A divided by B, treat B not like 20, treat it like 20.0, so that I retain that precision, that 1/2 part. Okay? Let's go ahead and see that it now actually works. Instead of 0, you get the correct answer of 0.5. Now you might be thinking to yourself, that's kind of stupid then. Why don't we just use doubles all the time, right? And we've seen why we don't use doubles all the time. What is 1/3 plus 1/3 plus 1/3 in math? 1. 1 and 8 in computers in computing, right? It is 0.999999, right? And when we need absolute precision for whole numbers, when we're modeling something that is whole numbers, like say number of students, you need an integer. Right? So not all languages are like this. Some languages are called dynamically typed, meaning that the types can change. Right? If you assign it an integer, it becomes an integer. If you assign it a double, it becomes a double, and then you don't have these kind of issues. But any C-style syntax, statically typed language is going to be pretty much like this. Java is like this. C# is like this. C++, I think maybe Objective-C, I'm not sure, and a few others. Right? So it's just something that you have to deal with. I got a 0. I probably didn't typecast. Yeah, go ahead.
So going forward, is B now a double for like the rest of the program, or is it just like a one-line?
Nope, it's just for the purposes of that expression. It's still an integer. When you declare a variable, right, then its type is fixed for that scope. It can't change. Right? It is fixed.
So that tells it just to output.
That tells it to
Output it that as just once, and then if we
treat it just temporarily as a double, and then right after that expression is done, you're back at square one. Yep. Okay. All right. Let's see. We saw overflow before. Now let's look at another operator. What I'm going to do is I'm going to take this chunk of code here, and I'm going to cut and paste it and put it into our notes here so that you have it when we push it out to GitHub. How do you find this code? How do you find all of these nice notes if you need to reference them? Where are they? on the GitHub, right? And that link was in the week 1 retrospective. If you need it again, I'll put it in the week 2 retrospective. But otherwise, all the notes are there. The notes are there for the other 2 sections of this course as well as a bunch of other information. Other operators. There we go. You can use the division remainder operator. Right? This is also called the modulus, right? Which is a percent sign instead. Right? Oops. There we go. So how does this work? Here's an example. Right? What if I have 10, and we usually read this as mod 3, but it's integer division, so you can read it however you want. Go back to grade school and read it that way. 10 divided by 3. Now in grade school, you had not learned that there were fractions yet, right? Or in early grade school. So you said that, well, 3 goes into 10 how many times? 3 times. With a remainder of 1. Gives a remainder of 1. And so the value of that expression, oops, cancel that. The value of that expression ends up being 1. Let's look at some other examples. What if I have 10 mod 2? 10 divided by 2 results in 2 goes into 10 5 times. This result is always going to be the remainder. So what's the remainder here? 0. 10 mod, or let's go with 11 mod 2. Results in 1. Hey, those 2 results, if you divide by 2, they're only going to 2 options, 0, 1, right? What does that 0 or 1 tell you? Even or odd, right? What if you'd mod by something else? What if you go 10 mod 3 results in 10 divided by 3? Well, we already did that one, I guess. It results in 1, we already said. What about 11 mod 3? Results in 2, right? Why? Because 3 goes into 11 3 times with a remainder of 2. What about 12, mod 3? Results in 0, right? So if you divide by something, it tells you whether or not it's divisible by that thing, or it has divisible by that thing with a remainder of 1, or 2, or 3, or 4. Eventually you get back around to the original, right? Where the next value is then going to end up being evenly divided by it, right? For example, what if I went all the way to 15 mod 3? That's also going to be a remainder of 0, right? Other math stuff, right? So again, the math library has constants. One of those being pi, the other one being e. What is e? That's the natural exponent, 2.71, blah, 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 right? Whatever it is. You also have, say, trigonometric functions like sine. Oops, sorry. They're all 3-letter words. Cos, cosine, tan, tangent, right? We already saw square root and power. Pow, right? And log, right? Now, which is base e. There we go. The natural exponent. And so in other words, in other words, it is the natural log. Let me go into LaTeX mode here. Sorry. ln of x. There we go. There. Right? It's the natural log, ln. What if you want to switch it to a different logarithm base? Do you remember your logarithms? Right? There's a change of base formula that you can always just use this one function to get it done by computing a quotient of something, right? If you ever need it, then pull that change of base formula out. But remember, you may need to use the -lm flag to compile using the math library, right? It's a link into the math library. And again, for reasons. If you're interested in the history, I can point you to a link to see what it is. What else? Right. How would I know what else is in the math library? Go to it, right? You could do that. You could do this, right? And read, oh wow, thousands and thousands and thousands, not thousands, but hundreds of lines of code, right? There must be a better way.
It's at least 1,000 lines.
Yeah, to what, 1,500 lines of code? C math, right? Library, right? And W3C schools is not recommended. C++ is going to be okay there. Tutorials point probably not. I don't know. Maybe this one. No, that's French. Les maths. I assume that that's French. Right.
I don't know. I failed for it.
All right, what else is there? Ceiling, pow, right? Oh, hey, absolute value, right? Fabulous absolute value somewhere else, right? Fabs, right? Somewhere. And a whole bunch of other things there. So let's go ahead and play around with some of them, right? Let me go ahead and get rid of this since I already copied it over to the notes. Yeah, go ahead.
Is there a difference between fabs and absolute value?
Yep. Let's go ahead and find out what that is. So let's go ahead and create a double x is equal to 10.5 or negative 10.5, so that it actually does something, right? Double y is equal to abs of x, right? And now let's print f. Y is equal to percent f for a floating point number and the line and y. Right? Run that again. What's going to end up happening? So it gives you the absolute value, positive 10, but what happened to my fractional part? Gone, truncated. Why? Because abs is for integers. In fact, here's another trick. You can use what are called the man pages, the manual pages, right? Man, tell me all about abs, right? There's abs, labs, labs, IMAX labs, and a bunch of others, right? What is it good for? There's abs. What type of variable does it take? An integer. And therefore, it ends up cutting off this 0.5 and then giving you the absolute value of 10. Right? We don't want that. We want to be floating point abs. We want fabs. Right? When I do that, now that fractional part is retained. Right? So abs is for ints. Fabs is for doubles. There we go. What's another nice one? Fine, round. Right? Round a number, right? Well, ceiling is not rounding, floor is not rounding, but rounding is rounding. Oh, fine, round. Oh, it's not in here, but it is indeed in the math library. Maybe, I don't know. Man, round. Right. It's in the math library, right? So let me go ahead and restore this to just 10, and we'll go ahead and try to round it. Actually, I'll go ahead and go with 3.14159 there. What is pi rounded? 3. Why? Oops. Because you round down halfway. 3.0. What if it were 3.64 blah, blah, blah? What's it going to do? 4. Right? What if I wanted to round to another place? What if I wanted to round to, say, this one over here? Keep that in mind, right? We'll revisit that here in a moment. But what I want to do for now is talk a little bit more about formatting. Right? So recall that you can print output in a formatted manner using printf. Right? The three placeholders, right, are %d for integers, %f for floating point numbers for doubles, and %c for single characters for int, double, and char, respectively. You can also add modifiers to print more or fewer significant figures and to align output values. So what do I mean by that? Let's come over here and let's change this. Right? So printf, if I just go ahead and print out a floating point number, what is the default behavior here? We've witnessed this now several times. Oops, sorry, x. How many decimals of precision? You just said it? 6, right? 14159.0. I didn't specify 0, right? Well, you didn't specify anything, it's going to be 0, right? What if I print out more significant figures? To do that, I can add the following modifier to this. So between the % sign and the f, I will add 0.10. That says print out at least 10 significant figures to the right of the decimal place. Let's go ahead and compile that and run it. There we go. And I'll preserve this. Right? So, and make notes as we go along. Right? Defaults to 6 decimals of precision. Right? This one is going to be 10 decimals of precision. Right? And what did it do? It filled it in, right? 14159, those are the 5 decimals that I specified. After that, it placed 5 zeros. Why? Because you asked for 10 total. Right? What if you wanted fewer? Go ahead. Go. 2 decimals of precision. And it's only 1/4. Let's go one more. Example, that is. 3 decimals of precision. Predict what this is going to print out. 3.14 what? 14, well, what's the next decimal here?
2.
1 or 2. It ends up being 2. Deduce. What did it end up doing to the number? It ended up rounding it. Did it change it? Let's find out. Let's print out more decimals of precision after that. Did it change the number? No. It only rounded it for the formatting out of the output. Right? It does not change your number. If you want to round to a particular decimal place, you're going to need a different solution that we'll talk about here in a moment. Right? But otherwise, 3 decimals of precision may end up rounding, right, for you, but only in the formatting, right, not in the actual number. Okay. Let's go ahead and create another variable here called my checking account balance. I've got a whopping $132.26.5. Right?
That seems a bit too high.
That's too high. All right. Well, what's the wrong? Do I have in money generally? Do you have a half a penny? No, not in 2022, right? They used to have half pennies and hay pennies and stuff like that. They may still have them in certain countries. I don't know, but we don't have that, right? Let's find out let's go ahead and print that out and format it as money. Well, money begins with a $sign, right? And I'll go ahead and go F here and the line, right? And I'll print out my balance. There we go. And what's it going to end up doing by default, according to line 8? 6 digits of accuracy. Is that how we treat money? Nope. Let me go ahead and add some more end lines here. So there we go. Just so that we have some vertical white space here from the old stuff to this stuff. Okay. All right. So I want to round to the nearest penny. Let me try something. Double rounded balance is equal to round balance, and then let's print out the rounded balance. Right. Bad bank. They took my quarter, right, and penny, right? Did that round successfully? No. Why? Because what does round do? It rounds to the nearest whole number. So now when we look at functions, we'll learn one of the basic design principles. In fact, in engineering, the basic design principle is be lazy, right? If you can reuse a pre-existing solution in your prototyping phase at least, then you do it. If you can use off-the-shelf components, then you do it because it's going to be way cheaper, way easier in your design process. So let's not reinvent the wheel and write our own function, because we're certainly not there yet, to round to the nearest cent. Instead, let's use what we have. How could I modify, say, some values here in order to exploit the fact that we already have this off-the-shelf solution, this round, that rounds to the nearest whole number? It's not exactly what we want, but maybe we can modify it, tweak it a little bit in order to get exactly what we want. What if the period were over here instead, the decimal were over here? Would it work then? Yeah. The decimal's not there. What could we do to that number to make it so that the decimal is there? Yeah.
Multiply by 100.
Okay. Let's multiply that balance by 100. Right? Now, balance is a double times an integer. The result is going to be a double. We don't have a truncation issue here. If it makes you feel better, go ahead and put that 0, but it doesn't matter. Right? Let's see if that worked. Uh-oh. Generous bank now. Right? They didn't steal my quarter. Instead, they gave me $12,000.
You forgot to divide back.
Right, so how do we fix this after we're done with the actual rounding? By the way, did the rounding work? That 6 went up to a 7. Right? So the rounding worked. How do we now make it so that we're not giving away $12,000? Divide by another 100. Now again, double divided by an integer is going to be a double. If it makes you feel better, go ahead and put that 0 in there, but it's not necessary here. All right, cool trick. Except that the rounded balance there is still printing out those superfluous zeros. How can we modify this so it doesn't? 0.2f. Excellent. Let's create another balance. Big balance is equal to 1,900,000. What's the jackpot in the Powerball? 120 million or something like that. 120,739,415 and 45 cents. There we go. All right. Yeah. Is that too big for an integer? Nope. That's only 120 million. What is our limit on an integer again? About 2.147 billion. Right? All right, so let's print this out. Big balance and rounded balance. Does that look nicely formatted? I mean, it looks okay, but in a ledger book, is that what it should look like? Think about a ledger book. What do you, or a table of figures or something like that. What do you, and you've got a whole list of numbers. What do you generally do with all those numbers? You line them up how? With the decimal point. Right? So you can add another modifier. You can add a second modifier to specify the minimum number of columns to print. To do that, I'm going to go ahead and grab both of these. Right? There we go. And what I'm going to do is I'm going to put another number in front of the decimal point here. I'll put 12. That might not be enough. Let's go 15 on both of them. Right? So now what that is doing is that's saying print at least 15 columns. On this second number, how many columns do we actually have? Here, let's count them together. 1, 2, 3, 4, 5, 6, 7, 8, 9. The period counts 10, and then 11 and 12. I specified that you need at least 15 columns. So if we've got 12 in the number, we've got 3 left over to play with. What it's going to end up doing is printing 3 spaces in front of all of that. And now they're all lined up, right? 1, 2, 3. Why so much space here? I did the same thing. At least 15 columns, right? Well, 1, 2, 3, that's only 3 decimals. The period counts 4, and 10, 2, 7, that's going to be a total of 6. So 15 minus 6, how many left over?
11.
15 minus 6? 9, right? Oops. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? It'll pad it out with a bunch of spaces. If you want to get crazy, you can go as large as you want, 30. Now it's getting too crazy because now it's way over there, right? And any number with only 17 digits of precision, at most you would need like 20 or something. So let me go ahead and restore that. Right? So that's a way that you can do nicely formatted output to the standard output. Now in real life, if you are presenting numbers to a user, an end user, an actual human user, you're probably going to want a web page or some sort of nice looking app with bright shiny buttons and stuff like that and stuff. And so you're talking about formatting something in HTML, or you're talking about formatting it in something completely different. But the principle still holds, right? You want to make your formatting look nice. One thing that we don't have here is commas, right? It's really still difficult to read this number as a currency because you don't have 1, 2, 0, comma, 739 comma, right, to denote each one of those three places. So you're going to have to get way fancier if you want to actually, produce output that looks nice to an end user consumer, right? This is as far as we go from the command line, though. Right? Questions about this so far? No? Okay. Then, I'll make sure that you have this in the notes. All right. And there we go. All right. You have all that in the notes now. All right. So let's talk about non-interactive input. So let's start writing a program here. In fact, I'm going to start with a brand new file. I'll go quadratics.c. I don't know. Yeah, let's go ahead and do it. I think I've done this before, but all right. So we're now in week 2. We've got 1.5 weeks here. What goes at the top of every program? Main. Well, before the main. The author header, right? So me, 2022 08 30, right? And the purpose of this program. The purpose of writing out the purpose of the program also gives you like kind of a roadmap. What the hell am I doing, right? Why am I writing this program? Put it in plain English to remind yourself of what you're doing so that you don't lose the forest for the trees, so that you have a nice roadmap going forward. This program reads in 3 values, A, B, and C, of a quadratic polynomial. Right? And this is the classic quadratic polynomial. A times x squared plus bx plus c is equal to 0. And outputs the roots of it, right? The solutions to x, right? So we all know quadratic formula at least, right? Good? All right. So we know what we're doing here, right? What comes next? Say what? Preprocessor directives. So I'm probably going to want to do some input-output, right? So I'm going to want the input-output library. Also, even though it's probably included for me, is going to be the standard library. And the standard input-output library. And if I'm going to be doing really sophisticated math like square roots, then what else should I need? Who do I need? Math. The math library. Right? Now comes main. Int. Main, int, arg, c, char, arg, v. Cut and paste that from any example that we've done so far. Return 0. There. That's your main shell of a program. Right? In fact, in week 5, in a few weeks when you go to do your first exam, I always recommend people to have an empty dummy file like this up so that you can go ahead and not have to deal with that boilerplate stuff, and then you just start not from scratch, but from a program that looks like this, of course, without the comments or anything like that. Right? I don't know how it's going to go yet. I mean, you might have a larger window of time than just this, like 1 hour or something. Right? Okay. All right. I want to. What's my first step here? Let's prompt the user for values A, B, and C. Okay. So I need to have 3 variables, right? Should they be integers? Remember that it's these are the coefficients for a quadratic equation. Are coefficients for a quadratic equation only ever integers? No. Nope. So if we want to support doubles, we should do what? Make them into doubles. Right? Now let's so declare my variables. Now let's prompt the user for values A, B, and C. If we want them to read anything, we have to ask them first, right? Please enter A. Right? And then scanf. What's the placeholder for a double when you're using scanf? %LF. Right? And we'll read in A. Is that correct? Let's ask the compiler. Not demo, but quadratic. Nope. What's it reminding me here about? The ampersand, exactly. The and sign, ampersand. And if I do that, then the compiler stops complaining. All right. copy, paste, copy, paste, copy, paste. Change, enter B, please. Enter C, please, and enter C, please. Right. Good? Why? What happened? In my copy, we call that copy paste, but we also in computer science we call it copy pasta. Copy pasta leads to spaghetti code. Spaghetti code is unreadable, mismanaged garbage that you can. Why do we call it spaghetti code? Think about cooked spaghetti, right? Can you tell one noodle from another noodle? Nope. With spaghetti code, you can't tell one line of code from another line of code. Right? It's unreadable. So don't get into that habit of copy paste, copy paste, copy pasta. Right? Because inevitably you will forget to replace one thing. Right? There we go. All right, that looks good. Now let's go ahead and print out, printf, the roots of %d x squared plus, not %d, what's my placeholder for a floating point number? F, %f x plus %f end the line, or r, dot, 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 end the line. Let me just go ahead and print out A, B, and C to make sure that I'm reading them up to this point. Okay. Please enter A, 10, 20, 30. The roots of 10, x squared, plus 20x, plus 30 are, dot, dot, dot. Right? I'm iteratively developing this, right? I'm making some sanity checks. Does it actually, I write 6 lines of code. Does it compile? Does it work? Right? All right, great, it works. Let's move on to the next 6 lines of code. Does that work? Compile it, test it, find out, right? I'm iteratively developing this. So as beginners, then that's what you do, right? That you want to only go a little bit, because if I write 100 lines of code and then start compiling and then start testing, I've missed like 20 bugs along the way, right? But if you only do small chunks at a time, then the likelihood that you'll have 20 bugs at the end is greatly reduced. Right? And then you don't have to go hunting for 20 bugs among 100 lines of code. You only have to worry about 6 lines of code at a time. 6 is just a number I threw out there. Right? It could be 10. It could be 1 line of code or something like that. Right? But go iteratively. Right? Sanity checks, testing. This is called ad hoc testing, right? Where you compile it and just test it really quick. Okay, everything seems to work. I'll do some formal testing later on, which will be introduced after the first exam. Right? All right, how do I compute those roots? How many roots are there, first of all? 2, right? Because it's a polynomial of degree 2, right? If it was a polynomial of degree 1, you would have a linear equation. ax is equal to, or ax plus b is equal to 0. Well, you just take b onto the other side and divide by a, right? And that's your solution. But here we need that quadratic formula from before. Root 1 is equal to b minus square root of, help me out here, b times b minus 4 times a times c, right? All divided by 2 times a. What was my mistake from before? Parentheses, 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 parentheses. Right? Now that's one root. That's the minus root, right? If you want the other root, what should it be? Plus. Now I've committed the sins that I told you not to commit. I've created variables called A, B, and C. Terrible variable names. I've created root 1, root 2, right? Terrible variable names. Except when that's it, right? Can you think of any other great names for a root? The first root, the second root? I guess you could say the first root, right? That's a little bit too verbose there. The first root of a quadratic polynomial, right? No. Right. Keep it simple. There's another acronym for you. You've probably heard it before. KISS, KISS. Keep it simple, stupid, right? Or keep it stupid simple, right? That's a little bit better. Right? Root 1, root 2 is good enough. Right? In fact, again, there's only 2 difficult things in computer science, right? Cache invalidation and naming things, right? Don't get hung up on the names. Right? As long as you've got a reasonable variable name, and these are certainly reasonable variable names. If I'm doing math stuff, The coefficients are always a, b, and c. Roots are always going to be roots, right? Then they're not representing money. They're not like the balance was. It's not representing the number of students, right? It's just representing this abstract idea, okay? R, and then let's go ahead and go with another print statement, printf, %f and %f, end the line. Root 1 and root 2. Oops. Now that I'm actually using the math, square root, what do I need? Math library hyphen lm. And I need to do what? Spell it correctly. That was really difficult to see. Thankfully, my compiler found it, right? That was probably really difficult to see that it was wrong. Thankfully, the compiler said, what? That should probably be printf, and it's not. Look really closely, and you'll see that the T is an I, right? Printf. There we go. All right. Let's run this again. Let's go 10, 20, and I'll go 3. All right. Oh, the roots are 0.16, 1.83. To be a sanity check, you have to make sure that you're sane, right? Does it work? Well, it gave me numbers. Is that enough to say that it works? Well, it's enough to say that it works, but is it enough to say that it's correct? Nope. Suggestions on how to verify this. Pull out your calculator. Do it. Or don't pull out your calculator. Go to Wolfram Alpha. Right? And roots of, what was it, 10x squared plus, what was it? I did 20 to keep b large intentionally. X plus 3. All right, well, it won't give me those numerically, but that's okay. Negative 183666666. Negative 183. Oh, negative. No, it's not negative. All right. Let's say it again.
When you define the roots of the quadratic, it's supposed to be negative b, not positive.
Oh, thank you. What's wrong? Formula is wrong. You didn't call me out the first time we did this either. Come on. Call me out on it. There we go. Negative b, right? All that'll do is swap those two around. It'll still be the same numbers and magnitude, right? There we go. Oh, dang it. 10, 23. There we go. Negative 183, negative 1633, and that's the other one. Negative 16333. There's my sanity check. And that's why I need a sanity check, right? That's why I need to check a secondary resource here to find those bugs before I move on. Right? Good. Any questions on that program? Because now let's change it. Right? Actually, before we go on, sanity check. Is there a way that I could break this? Okay. Divide by 0. Where am I dividing by 0? A. What if I gave it A? Right, and then we know that 20 and 3 are already okay. What's going to happen? Inf negative nan. Right? Negative inf negative nan. Right? It actually didn't kill the program in this case. Right? So I don't know why, but it gave me garbage results. What's another way that I could break this program? And by the way, why does that break it besides division by 0? If you have a coefficient of 0 here, do you have a quadratic? Nope. What do you have? A linear function whose solution is negative c divided by b. Right? Okay. Question?
Oh, no, I was going to say, like, can we enter a variable then?
Yeah, you could reprompt them. Like, you can't enter 0, man. You can't do that to me, right? Or you could do something else. Or, like, for example, oh, you meant that you wanted to solve a linear equation. Okay, we'll do that for you, and we'll do some different logic to solve that negative c divided by b, right? Or you could say print an error message and say, nope, I'm gonna die right now because I don't know how to deal with that. Run me again and try and enter good input. Those are decisions, right? If we're gonna make those kind of decisions, we need conditionals, which we'll talk about on Thursday. Question?
It's another way that you can break the program.
All right, good. Go ahead.
You could enter something that isn't a number.
All right, let's try it. 30. There we go. 3. Oh, then it immediately dies. It doesn't even prompt me for C, right? Right. Why? Because it sees T. It says that's not a number. So what have I read for so far? 0. And by the way, the entire input buffer is still full, and so it fails to move on, right? We'd have to flush that buffer. Lots of other stuff is going on under the hood. That's why we need to get rid of this interactive input. And that's what we'll do here in a second. But before we do that, let's break it one more time. Yeah,
Try and get a negative number onto the radical.
good. What would that be? All we have to do is make b really small, right? 10, 1, and 10. Not a number, not a number, right? Because we are taking the square root of a negative number. Right? So in order to take care of all these degenerative corner cases, what we need is some defensive programming. We need to check for these error conditions before we actually do them. And to do that, we need, again, conditionals on Thursday. For now, though, what I want to do is I want to get rid of these prompts. I don't want an interactive program. I want to just give these inputs as part of the command line execution of a.out. I want to do something like this. Make sure that it works. So 10, 20, and 3. Right? There's my original input. Right? I want to just give those 3 numbers as part of my command line execution. Right? It's not going to do that right yet because I haven't recompiled it. So how could we do that instead? Right? We can use this argc and this argv up here. Those are the arguments. Whenever I provide additional arguments here from the command line, those are sent into the program via this thing up here, argv. It's argvector, right? And this is a little bit of a preview of arrays and strings later that we'll get to in much more depth later on. Just understand that the first one is at argv sub 0, right? This is always going to be the here. Let me go ahead and do it over here, non-interactive. You can provide command line arguments. Sometimes we'll call these CLAs instead of using interactive input. Right? The arguments are passed on the command line as ./a.out, A, B, and C. Right? Delimited by spaces. Right? The program has access to them through the argv argument vector. Right? The first one is at argv sub 0, right? And is always the executable file name. In other words, a.out. Right? If you compiled this into another file called my awesome super spectacular program, then instead of a.out, it would be my awesome super spectacular program. Right? Usually you're going to be a.out though, so you ignore it, right? Ignore it and move on. The second and user provided and first user provided is at argv sub 1. Right? Well, you go up from there. The third is at argv sub 2. Oops. Format that. There we go. Third, right, is, there we go. And just predict, where would the fourth be? argv sub 3, etc., etc. Right? So how do you know how many there are? argc tells you how many arguments were provided. Right? It is the argument count. Right? And that's why it's a C, argc. Right? We can play around with that here in a little bit, but let's go ahead and finish this program. Right? I want to convert the first user-provided command line argument, CLA, to a double. Right? Well, where is the first user-provided one? At argv sub 1. Right? So argv sub 1. Right? argv sub 1 is not a double. Right? I cannot do something like this. A is equal to that. Let's find out why. The compiler is going to really complain about this. It's a full-on error, right? argv is a char star star. I wonder what that is. Right? It's a character array. Right? It's a string. Those are incompatible. I need to get a string, the string 1, 0, or whatever it happens to be, and I need to convert that to the number 10, 1, 0. Right? To do that, I use a function called a to f. A to f stands for alphanumeric to floating point number. Right? And I can do that for all of them. How do I convert the second one? Convert the second. It would be B is A to F of argv sub 2. And the third, C is equal to A to F of argv sub 3. Right, there we go. And now I can read those in. Let me go ahead and just compile this and make sure that it works to demonstrate it. Now, 10, 20, and 3. And we get the same exact results as before. But you know, it was non-interactive. Did it prompt me for anything and let me mash my keyboard, hit enter? Right? Did it let me enter in 30, THIRTY? No. Instead, I provided numbers at the command line. What happens if I do 33? Then I end up with 0. Right? 30 is no number that it can convert. So A to F, 0. Right? What if I don't provide all the command line arguments? 10, 20, but not the third. So it's going to end up converting the first successfully, the second successfully. When it tries to convert the third one, it's not there. And if it's not there and it can't do anything with it, what do you think happens to it? Yep. Segmentation fault, core dump. A segmentation fault, segmentation is a segment of memory. That segment of memory doesn't belong to you or your program. And the operating system sees that you are trying to access an illegal part of memory, and it will fault you out and kill the program because that's dangerous, right? Imagine if you could write any program to read any part of memory of the computer, including the parts that, say, are storing secret keys or GitHub passwords or whatever, right? Then if you can arbitrarily read any part of memory, you can get access to that kind of stuff, and it's this huge security hole and risk. Right? So the operating system sees that you're trying to do something illegal and kills it accordingly. Right? How could we check to make sure that they provided enough command line arguments? argc. Argc should be what? Should it be 3? 4. Why? That 0 is always going to be the executable file name. Then A, then B, then C. So if, here, let me put it in plain English. If argc is 4, we are good. If it is not 4, we're not good. Right, ... Right? So let me go ahead and translate that into C code. And this is a preview of Thursday and the last thing that we'll do here. If argc is not equal to 4, then we will print an error message. Printf, you need to provide 3 arguments, ... end the line. Right? And we'll exit on them prematurely so that none of this code down here below is executed. We will simply just quit out of the program entirely. Right? Don't worry about that one yet. We'll talk about exit codes later. So I only provide 2 command line arguments instead of, actually, am I providing only 2? 2 user provided, but a.out is 3, and so it's not equal to 4, and so we say, no, you need to provide 3 arguments. Right? What if I provided 3? It works. What if I provided 4, or 5, or 6, or 7? It's also going to error out here. I don't know what to do with that crap. Right? I'm just going to go ahead and error out and quit on you. Right? Now, for your first hack, you don't need to worry about this. The grader will always provide the correct number of command line arguments, so you don't need to check for this. If you want to write code to do this, go ahead. In the future, after we've covered conditionals, then you will need to write defensive code and error checking like this. All right, I'll see you over in lab 1 in about 15 minutes. Well, for those in the 1:30.